Welcome to Physics for Everyone. Today we learn about continuous X-ray spectra. First, X-ray spectra and its two parts. What are they? Continuous X-ray spectra, characteristic X-ray spectra. Then we learn the explanation for continuous X-ray spectra in this video. In the next video, we will be learning about characteristics X-ray spectra and its properties. Then we learn brimstone or breaking radiation, and we learn cutoff wavelength. Finally, we learn do-one Hunt formula in this session. X-rays are produced when fast-moving electron strikes a metal target. If we analyze the wavelength in X-ray coming from Coolidge tube and plot the intensity of X-rays with its wavelength, look at the graph. For tungsten at 35 kilovolt, we get a curve. And for molybdenum, for the same accelerating potential, 35 kilovolt, we get another curve. Here we have two peaks. The X-ray spectra of tungsten and molybdenum at a particular accelerating voltage is given here in the graph. Lambda naught is the cutoff wavelength. We learn more about cutoff wavelength later in the cases. X-ray spectra consist of two parts. One, a continuous spectrum, that is a gradual change in the intensity of X-ray with respect to wavelength. Then second, a series of peaks superimposed on this continuous spectra. These peaks are called as characteristics X-ray spectra. Let us learn about continuous X-ray spectra, a gradual change in intensity with respect to wavelength. Here for tungsten at 20 kilovolt, we have a curve. Next, for 30 kilovolt, we have another curve. For the next 40 kilovolt, we have another curve. And finally, we have for 50 kilovolt, we have another curve. As this accelerating potential increases, the cutoff wavelength, the minimum wavelength, decreases, okay, going towards the side of origin. The X-ray spectra of tungsten at various accelerating voltages are given. The continuous spectrum consists of radiation of all possible wavelengths with a minimum wavelength lambda naught, which depends only on the voltage across the electrode but not on the target material. So look at, I read it again. The continuous spectrum consists of radiation of all possible wavelengths with a certain minimum wavelength lambda naught, which depends on the voltage across the electrode but not on the target material. So lambda naught, we call it as lambda minimum. We call this as cutoff wavelength. Let us look at characteristics spectrum. Here we have it for molybdenum. Here there are two peaks on the continuous spectra of molybdenum. These two peaks, high intensity of X-ray at a particular wavelength. At few particular wavelength, we have a sudden increase of intensity of X-ray. These sudden increase in intensity, okay, we call it as characteristic X-ray spectra, and it is the nature of the material, the target material. The peaks are characteristics of the material of the target, and hence it is called characteristic spectrum. Explanation. Here you have a nucleus, first orbit with 2 electron, second orbit with 8 electron, and third orbit with few electron. In this, okay, a target material, an electron goes. As it goes, its initial energy is E1, final energy is E2. The E2, the final energy, is less than the initial energy. The loss in energy, right, appear in the form of photon of energy h nu, which is equal to E1 minus E2, energy of the emitted photon. Let us go for the detailed explanation. When a fast-moving electron penetrates and approaches a target nucleus, the interaction between the electron and the nucleus either accelerate or decelerates the electron, which results in the change in path of the electron, and the loss appears in the form of photon. The radiation produced from such deceleration electron is called brimstone or breaking radiation. The energy of the photon emitted is equal to the loss of kinetic energy of the electron. Right? The energy of the photon emitted is equal to the loss of kinetic energy of the electron. And this is very important point what we are going to learn here. Since an electron may lose a part of its energy or all of its energy, so that when it loses all of its energy, then the photon will have a highest energy, right? When the electron loses part of its energy, then the emitted photon will have less energy. So the photons are emitted with all possible energy, with all possible frequency, with all possible wavelength, with a cutoff wavelength as the minimum wavelength. This continuous spectrum is due to the radiation. The continuous X-ray spectrum is due to such radiation. So H nu equals the energy, that is equal to EV. So let us write Hc by lambda. We replace frequency as velocity by wavelength equals EV. So let us find wavelength lambda equals Hc by EV. So the EV value, no, that EV value may vary from 0 to the highest value E capital V. So the energy of the electron varies from 0 to EV. The loss of energy is varies from 0 to EV. Right? Very good. Therefore, the lambda, the wavelength, lies between infinity to Hc by EV. When the energy loss is 0, right, then the lambda will have a maximum value that's called infinity. As the value EV increases towards EV, then the emitted wavelength will be lesser and lesser, right? And it will be equal to Hc by EV. This explains the origin of continuous X-ray spectra and cutoff wavelength. Lambda naught equals Hc by EV. Here there is no loss of energy. All the energy of the electron completely converted into photon, right? And H lambda naught equal to Hc by EV, where lambda naught is called the cutoff wavelength. When an electron gives up all its energy, then the photon is emitted with the highest frequency nu naught or the lowest wavelength lambda naught. Substituting the values of H, C and E, we get lambda naught equal to 12,400 by V Armstrong unit. The relation given by this equation is known as Duan-Hunt formula. Duan-Hunt formula, lambda naught equal to Hc by EV. Let us substituting the value, we get lambda naught equals 12,400 Armstrong unit by capital V. The value of lambda naught depends only on the accelerating potential but not on the nature of target. This is in good agreement with the experimental result. Thus, the production of continuous X-ray spectra and the origin of cutoff wavelength has been explained on the basis of photon theory of radiation. Thank you, children.